Swayam Prabha. Digital India. Educated India.
Welcome to lecture 31 of the course on multivariate data mining methods and applications. The title of this lecture is Self-Organizing Map. Self-organizing map is a neural network, a simple neural network which has just input layer and output layer. It does not have any hidden layer. In self-organizing map, the observations are arranged in a two-dimensional grid. Actually, the observations belonging to a particular grid show nearby pattern. So, we can use self-organizing map for different purposes, like we can use self-organizing map for dimensionality reduction. We represent high dimensional data into low dimensional grids. So, just like the principal component analysis, we are able to reduce the dimension of the high dimensional data using self-organizing map. Then we can also use self-organizing map for topological ordering. In self-organizing map, actually nearby points have more similar patterns, so it can be used for topological ordering. We can also use the self-organizing map for clustering purpose and for data visualization. So, now we are going to discuss the architecture of self-organizing map and its various applications also. Self-organizing map, which is also called Kohanen self-organizing feature map or Kohanen neural network. This is an artificial neural network and it is trained using unsupervised learning to produce a low dimensional representation of the input space. So, as I mentioned earlier, the self-organizing map has just two layers, input layer and output layer, and it does not have any hidden layer. Then it is trained using unsupervised learning, because you do not know which observation belongs to which particular grid. This information is not given while training the model. Then self-organizing map is consist of a grid of nodes. You have a grid of nodes with each node associated with a weight vector of the same dimensionality as the input data. And then the outcomes are not predetermined. And since the outcomes are not predetermined, it is an unsupervised learning scheme. Further, it does not have any hidden layers, it has just input and output layers. So, since it does not have any hidden layer and it has just input and output layers, it is easier to train. And in output, actually, only the winning node appears, or you can say only the winning node fires. So, it is a relatively simple network and can be trained very rapidly. Further, the objective is to transform a high dimensional data input space into a low dimensional, say usually 2-dimensional discrete output space. So, although you have very high dimensional data, your output space is usually 2-dimensional. Topology in the data is preserved, but not the actual distances. So, while reducing the dimension, we keep the topology in the data, but not the actual distances. Then spatial locations of the nodes in the output space indicate inherent statistical features contained in the input space. So, in the output space, you have nodes at different spatial locations, and these spatial locations actually indicate different inherent statistical features contained in the input space. And usually we take the SOM grid as rectangular or hexagonal. In fact, in practice, we usually prefer hexagonal grid. In rectangular topology, if grids are rectangular, each internal node has 4 neighbors, whereas in hexagonal topology, each node has 6 neighbors. So, hexagonal structure is preferred as it displays greater variance in neighborhood size. With hexagonal topology, you can have 6 neighbors. So, it displays greater variance in neighborhood size. So, here we have hexagonal topology. In fact, we will discuss this example in detail later on, but here we have applied SOM algorithm to IRIS data set, and we get this kind of map. We will again come to this example later on. Again, in this figure, we have rectangular grids, whereas in this figure, we have hexagonal grids. So, in rectangular grids, you have 4 neighbors, whereas in hexagonal grids, you have 6 neighbors. Now, the advantages of SOM are there is no assumption about the distributions of variables or independence among variables. So, you do not require any such assumption. You do not require any assumption about the distribution of variables, or you do not even require the assumption that the variables are independent of each other. Further, you can easily implement the SOM algorithm even to solve complex non-linear problems. So, this is a big advantage. Even if your problem is non-linear in nature, the algorithm is so simple or such that it can be easily implemented. It can effectively handle noisy and missing data. You remember that clustering, in most of the clustering algorithms, if you have noisy or missing data, then those methods, those algorithms fail, or those algorithms create problem. But with the self-organizing map, you can easily handle data which is noisy, or even if some of the observations are missing. Further, you can easily handle big size samples. So, it is quite easy to implement the algorithm even for the big size samples, or even if you have to solve complex nonlinear problems. Now, here are the applications of self-organizing map. It is used for dimensionality reduction. You can use it for the dimensionality reduction. Further, you can also use it for the clustering purpose, or for data visualization and for pattern recognition. So, we have high dimensional data, we want to reduce the dimension of the data, and if you apply principal component analysis, the usual principal component analysis, then it is linear in nature. And if you are using kernel based principal component analysis, it is quite complex. But self-organizing map can handle even nonlinear problems of dimensionality reduction without much problem. It can handle complex problems. Further, in clustering also it can be used, or for data visualization also it can be used. It is particularly useful for exploring and understanding high dimensional data to reveal underlying patterns and relationships in an interpretable manner. So, for exploring the high dimensional data, or for pattern recognition of high dimensional data, you can use it. It has applications in industrial instrumentation, pattern recognition, even in process control also it is used, and in robotics. It is also used in telecommunications or in the field of medical. So, it has medical applications also. For optimization and product management also, one can use self-organizing map. So, it has various applications in different fields. Now, here are the training steps. First, we initialize the weights. Weights are randomly initialized. Then, for training purpose, we present input samples to the self-organizing map, and we adjust the weights to better match the input patterns using the following steps. Say, we do the neighborhood selection. A neighborhood around the best matching unit is selected, and the best matching unit is the node whose weight vector is closest to the input sample in the input space. So, what you have done? You have initialized the weights randomly. and then you are presenting the input sample to SOM. And then we adjust the weights so that the weights better match the input sample or input pattern. And for that purpose, first we select the neighborhood around the best matching unit. That is the node whose weight vector is closest to the input sample in the input space. And then we update the weights. The weights of the nodes within the selected neighborhood are updated to be more similar to the input sample. And after updating the weights, we again go to the first step, training process. We again go to the training process, and we go to the training process, or we iterate the process for a fixed number of iterations or until we achieve the convergence. Now we consider two versions of the SOM algorithm. First is online version and the second one is batch version. In online version of SOM, we present the items of the learning set or observations of the learning set in sequential fashion. We present the items one by one, and then we update the weights. In batch version, we present all the data together at a time. We have two-dimensional grid and then we present all the data at a time. Now, suppose in the grid there are K1 rows and K2 columns. This K1 denotes the set of rows and this K2 denotes the set of columns. So, K1 is the set of numbers 1, 2, so on capital K1, and K2 is the set of numbers 1, 2, capital K2. And the number of rows and number of columns K1 and K2 are chosen by the users. Then the total number of nodes is K1 into K2. Say, suppose you have this rectangular grid. Then how many rows are there? 3. So, K1 is equal to 3 and number of columns is 5. And total number of nodes is 15, 3 into 5. Now, suppose L1, L2 belongs to K1 cross K2 and this is a particular node. Say, suppose this node. So, this is a particular node. This node is in second row. So, L1 is equal to 2. And in second column also. So, L2 is also 2. Then initially select K1, K2 to be much larger than the number of clusters. And then we reduce the number of row and column nodes. Now, we select a particular node L1, L2 belonging to K1 cross K2 as say K equal to L1 minus 1 capital K2 plus L2 which belongs to this k. Say in previous example, you have k1 equal to 3 and k2 equal to 5. Now, suppose you take a particular node, say 2, 3. Then what is the value of k? L1 minus 1, that is 2 minus 1 or 1 into k2, 5 plus L2. L2 is 3. So, you have 8th cell. Similarly, you can order the other cells also, and ultimately we take this k as the set of all cells 1 to capital K. Then in SOM, kth node is represented by a vector, say mk, belonging to RR. And this vector mk is called the synaptic weight vector. So, these vectors mk for all k are called the synaptic weight vectors, or these are also called prototypes. We also use the term prototypes for mk's, or sometimes we use codebook vectors, or sometimes the term reference vectors or model vectors for mk. But mostly mk's are called prototypes or synaptic weight vectors. Now we come to the online version first. First we set the map size k1, k2. Then we initialize all representatives mk or all prototypes mk's for k equal to 1 to capital K. So, each mk is a random vector. Then an input vector x is randomly selected from the data set or the learning set. Suppose you have the learning set L, then you select an input vector from this learning set randomly. And usually we standardize all the input vectors to make the mean 0 and variance 1. And then we present the standardized x to SOM algorithm. Now, we have earlier also used the same notation for Euclidean distance. So, we are using this notation for Euclidean distance. Now, suppose k star is equal to argument minimum k norm of x minus mk. Then mk star is declared as winner, and k star is the best matching unit of winning node. So, what we do? We have the input vector x, and then we consider the prototypes mk's, which are initially selected randomly. For each k, we take the norm of x minus mk, and then we try to find out the value of k for which this norm is minimum, or the node. Remember that a node is represented by the prototype, that is kth node is represented by mk. So, when we say that x is closest to a particular node, we mean that x is closest to the corresponding prototype. And to measure the closeness, we take this Euclidean distance between x and mk, and then we try to find out the value of k for which this Euclidean distance is minimum, or we try to find out the prototype mk which is closest to x. And suppose for k equal to k star, this Euclidean distance is minimum, then mk star is declared as the winner or best matching unit or winning node. For x, this particular node is the winning node or the best matching unit. Next, we consider those nodes which are neighbors of the winning node. So, now we move to the neighbors of the winning node, and k dash belonging to k is a grid neighbor of k star belonging to k. If norm of mk star minus mk dash is less than or equal to c, we take a threshold value c, and if norm of mk star minus mk dash is less than or equal to c, then we say that k dash is grid neighbor of k star. Now, suppose NCK star is the set of grid neighbors of winning node k star. Then NCK star is actually the neighborhood set. Then, after making the assignment, after assigning x to a particular winning node, we update representatives corresponding to each grid neighbor of k star. Not only the representatives of the winning node, means we are going to include k star also. So, we update the mk star, but we also update the representatives, means mk for each grid node in the neighbor of k star. So, we update mk, the updated mk is equal to mk plus alpha x minus mk, where k belongs to NC k star. Alpha, which lies between 0 and 1, is the learning rate factor. So, this is how we update the prototypes. Now, if k does not belong to NC k star, k does not belong to the neighborhood set of k star, we select alpha equal to 0. So that mk for k not NC k star remains unchanged. So, we only update the values of mk which belong to the C neighborhood of k star. Of course, it also includes k star. Then we repeat the process a large number of times, running through collection of input vectors one at a time. So, we present the observations one by one, and we repeat the process a large number of times. So, we run the algorithm at least 500 times the number of nodes. Now we consider the distance weighted version of the SOM algorithm. Notice that in the previous SOM algorithm, we have used the norm of x minus mk to measure the nearness between x and mk. Now here we are using a neighborhood function. Say this is the neighborhood function, and this neighborhood function depends upon how close x to mk. And then we update mk as mk plus alpha hkx minus mk. H is the neighborhood function, and one may take hk equal to exponential minus norm x minus mk star square divided by twice sigma square into indicator function that k belongs to nck star. So obviously, if k does not belong to the neighborhood of k star, then hk is equal to 0 and mk remains unchanged. We modify mk only in the neighborhood of k star. Then hk defined here is the multivariate Gaussian kernel function. Sigma is the neighborhood radius, and alpha equal to alpha t, where t is the number of iterations. So this alpha depends upon the number of iterations also. Usually as t increases, alpha varies from large initial value to a value slightly greater than 0. So this is how we vary alpha. Now suppose t is the maximum number of iterations and alpha naught is the initial learning rate. Then some of the commonly used learning rates are, say, linear learning rate, in which alpha t is equal to alpha naught into 1 minus t by capital T, or power learning rate, in which alpha t is equal to alpha naught into 0.005 upon alpha naught to the power t upon capital T, or inverse learning rate, in which alpha t is equal to alpha naught upon 1 plus 100 small t upon capital T. Here is the plot of all the three learning rates. So the graphs of learning rates alpha t for the linear, power and inverse forms. And then we have taken the initial learning rate alpha naught equal to 0.5 and the total number of iterations capital T equal to 100. So this is the linear learning rate, and then we have inverse learning rate here and power learning rate here. So these are the plots of three learning rates. Then we consider the batch version. The batch version is actually much faster than the online version. In online version, we present the observations one by one. We select the observations from the learning set randomly and then we present the observations sequentially. In batch version, we present all the observations at a time. And then the algorithm for batch version is, first we initialize MKs. For a particular MK, we list all Xi's whose MK star belongs to NCK. So MK star belongs to NCK means K star is in the neighborhood of K. Then update MK by averaging the items obtained from the previous step. Then one may take weighted average with weights Hik star, that is Gaussian kernel, as weighting function. So this is how we update MKs. Then here nodes are drawn as circles and data points mapped to a node are plotted within the circles corresponding to that particular node. Now we consider the unified distance matrix, that is U matrix. The U matrix is constructed by calculating the distances between neighboring neurons in the SOM grid. And then these distances are visualized as a grid of values using a grayscale or color scale. And this U matrix is in particular useful for visualizing the clustering structure and the smoothness of the SOM. Say areas of low values, and we may represent the areas of low values by dark regions. So these dark regions indicate regions where neurons are close together in the input space. And if neurons are close together, it means the presence of clusters or similar patterns. Then the areas of high values of U matrix, and we usually indicate the areas of high values by light color or light regions. So the high values indicate regions where neurons are far apart, and then these neurons represent transitions between different clusters or patterns. So U matrix actually helps in identifying the clusters or detecting the presence of outliers or assessing the overall topology of the SOM grids. Then in the input space, each entry is the Euclidean distance between neighboring representatives. For example, suppose M1, M2, M3, M4, M5 is a particular row of 5 nodes. Then U matrix is a 1 cross 9 vector. Say U equal to U1, U12, U2, U23, U3, U34, U4, U45. Now, Ui is a specific value. Say we define U3 equal to U23 plus U34 divided by 2. So actually, what is U3? U3 is the average distance from U3 to neighboring representatives U2 and U4. Then a small value in U matrix indicates that SOM nodes are close together in input space, and this actually indicates the presence of some cluster, and large value indicates that nodes are far apart through neighbor in output space. And usually we display U matrix in color map, and as I mentioned earlier, the small values of U matrix are denoted by darker colors. Hierarchical SOM. SOMs are used for dimensionality reduction and visualization of high dimensional data. Hierarchical SOMs provide a more structured organization of the data into multiple levels of abstraction. Basically, what you have a tree of maps. So, at the lower level, lower maps act as a pre-processing stage, and then nodes in each level of the hierarchy are themselves self-organizing maps. You have different levels of hierarchy, and if you consider a particular level of hierarchy, then you obtain a particular self-organizing map. So, basically what you have a tree of maps, a tree of self-organizing maps. Then hierarchical SOM enables to capture complex relationships within the data at different levels of granularity. Then the data is clustered and organized into smaller and more manageable groups at each level of the hierarchy. Now, we consider this example of Irish data set, and for constructing the self-organizing map, we have used AveSum package of R. And since we have already used Irish data set in many previous examples, so I am not going to describe the data set in detail. So, this is the program which I have used. Then once we apply self-organizing map, then you also want to measure the quality of the self-organizing map, and then to measure the quality of SOM, we use different measures like quantization error, which is the average square distance between the data points and the map's prototypes to which they are mapped. So, lower the value of quantization error is better. Then percentage of explained variance, which is equal to the share of total variance that is explained by the cluster, that is 1 minus quantization error divided by the total variance. So, obviously higher is the better. Then topographical error, which is the share of observations for which the best matching node is not a neighbor of the second best matching node. So, obviously lower is the better. 0 indicates excellent topographic representation. So, all best and second best matching nodes are neighbors. 1 is the maximum error. So, best and second best nodes are never neighbors. So, lower is the better. Then Kasky-Lagus error, which is the mean distance between points and their best matching prototypes, plus mean geodesic distance between the points and their second best matching prototype. And we define the geodesic distance as the pairwise prototype distances following the SOM grid. And then we have U plot also. So, in U plot darker cells are close to their neighbors. So these are the quality measures. Quantization error is 0.2210. Explained variance is 94.44%, which is quite high. Topographical error is 0.1733, quite low. And Kasky-Lagos error is 1.65. Then the number of observations per map cell. In all, actually, we have 16 cells, and this gives the number of observations per map cell. Then we have also used the superclasses of SOM. Cluster the SOM map into superclasses. So this is like hierarchical SOM. Groups of cells with similar profiles. So we have SOM map, and then we have cluster in the SOM map into superclasses. So basically we have two level hierarchy. Now here is the SOM map of all the observations. If we move the cursor to different grids, then we get the information about different nodes. Say this particular observation has sepal length 7.9, sepal width 3.8, petal length 6.4 and petal width 2. Further, this is the U matrix. Again, in the darker regions, the observations are more clustered or more close to each other. So this is the U matrix, and if we move the cursor to different nodes, we get the information and the observations in that node. You can even plot the pie chart in different nodes, or this is the SOM superclass. So in the superclass, you have 3 clusters denoted by 3 different colors, and in each superclass, when we move the cursor, we get the information about that cluster or that superclass. One can even plot the bar chart in different nodes. So in this lecture, we have discussed the self-organizing map, which can be used for topological ordering or for reducing the dimension of the data, or for data visualization, or even for clustering also. I am going to stop here. Thank you.
Hello, I am A.K. Sharma and I teach sociology in IIT Kanpur. I am attempting to answer a simple question, what is sociology? Now friends, one simple answer would be that sociology is a study of human behavior. And this study of human behavior has a history. Actually, due to growth of science, technology, and due to industrialization and economic development in the West, initially there was a hope that by application of science and technology, the face of this world can be changed to the advantage of mankind. But what was found or what was observed, that this did not happen. And despite economic development, urbanization, industrialization, surveys showed that poverty had increased, unemployment had increased, even health conditions became worse. And today you will be surprised to know that there was a time when death rate of urban areas was higher than the death rate of rural areas. Cities or the places of development, industrialization and education and enlightenment became consumers of rural population. So people started asking, why is it so? And some philosophers, engineers, mathematicians who contributed to emergence of a discipline like sociology started thinking that perhaps we need a new subject in which we will apply the same tools and techniques which are being used by scientists, mathematicians, physicists, chemists, but we will study human behavior. In other words, we will try to discover if there are laws of human behavior, and by applying those laws, perhaps in the future, the condition of mankind can be improved. This is how sociology developed. Initially, Auguste Comte called this social physics. He also used terms like social statics and social dynamics, the usual division of mathematics. And he believed that social statics will study relationship between different parts of society, and social dynamics will study relationship between parts of society and total society, change in total society. Now, you may ask that if sociology is the study of human behavior, there are many other branches of social sciences which study human behavior: economics, anthropology, psychology, etc., etc. The difference between sociology and these disciplines is that while in these disciplines we study one specific aspect of human behavior, like economics will study production and distribution of wealth, psychology will study cognitive processes or mental models or personality, social psychology will study personality, anthropology will study culture. Now, somebody has to relate one aspect of human behavior with the other aspects, or one social fact with the other. These are all social facts for us. And if somebody tries to link cognitive processes with economic conditions or urbanization or caste system or religion, or somebody tries to relate urbanization with human psyche, or somebody tries to correlate cultural context with economic behavior, then it becomes sociology. So, sociology combines different areas which are individually studied by different disciplines. And sociology also studies new questions which are not studied by any existing subject so far. So, like these days issues of waste disposal, entropy, environment, safety, urban places as new geomorphological systems come up, and we want to correlate one aspect of urbanization, say percentage of population living in urban areas, and risk, environmental risk, carbon dioxide, this emission, that emission. Now, which will be the first discipline to take interest in these things? Because sociology. So, sociology not only combines facts from different aspects of society, sociology also addresses new questions. And I can also say that one central feature of sociology is to explain individual behavior or individual psyche in terms of properties of larger society. In simple terms, if you imagine that there are two aspects of human behavior, individual and society, then while uh, other disciplines like psychology are focusing more on individual, we study characteristics of individuals in terms of certain characteristics of larger society. This is what sociology does. Sociology is very useful for planners. Sociology is useful for answering new questions, as I said, which have not been answered by any existing discipline. And I would say that sociology is especially helpful for self enlightenment or for developing empathy, because sociology only tells you that there are no right or wrong answers of social issues. It is not physics, it is not mathematics, it does not have fixed answers to issues, because questions can be looked at from variety of perspectives. So, role of perspectives, thinking, interest, power, etc., also come up uh, in, in answering social questions. And it is this aspect that something can be looked at from variety of perspective, that something can be looked at from the perspective of government, the same thing can be looked at entirely differently from the perspective of people or from the perspective of NGOs or from the perspective of experts. So, this realization, this takes us to self enlightenment and empathy. Thank you.
Hi, my name is Gillette Sam, and I teach sociology at IIT Kanpur. Today, I want to tell you a little bit about what sociology is. In order to go ahead and study sociology, one of the things you need to develop is a sociological way of thinking. Uh, Now, this capacity to think in a sociological manner was termed as the sociological imagination by an American sociologist called C. Wright Mills in 1959. He argued that in order to think in a sociological manner, you should be able to have two different skill sets. The first skill set would require you to have the capacity to think beyond the problems that individuals face. So, if you encounter a problem that some one individual is facing, you should be able to connect it to a broader public problem. Mills gave the example of people in his neighborhood. He says if there is one person who is unemployed in the neighborhood, that seems to be an individual problem. But as a sociologist, you're expected to dig around a little. So you come across a couple of other people in your neighborhood who are also unemployed. That indicates to you that rather than being a specific problem, there is a larger public issue at hand. So, as a sociologist, you're supposed to to look at individual problems and see how they are connected to broader public issues. The second capacity that you're expected to develop as a sociologist is the capacity to link an individual's biography with history. Historical thought may not come to you as the first thing that's connected to sociology, but it plays a pretty important role in the field. So Mills argues that rather than looking at a problem in the here and now, it's important to trace that long historical trajectory that may be connected to this individual problem. Let me give you an example from India, right? Um, let's say you look at the women in your family. Let's see at what age do they get married. So you may see that your sibling is getting married at the age of 25. Uh, Go back one generation. At what age did your mother get married? You may find that she got married a little younger, let's say 21. Go back another generation. At what age did your grandmother get married? You may find that she got married even younger, 18 or possibly even younger than that. So, this capacity to see how the history of a family then influences the age at which your sibling got married That is the capacity to bridge the biography of a person, or rather, by a biography, we can also think of the biography of a particular problem with history. What has happened in the past? How is that connected to this individual or this problem in the present? Thank you.